Today we discuss lability and inertness of metal ligand bond in coordination compounds. First is labile complex compounds. Which are labile complex compounds. If metal ligand bond breaks quickly, that is within few seconds. Then the starting complex compound is shared with the body. If the metal ligand bond breaks quickly, that is within few seconds, then the starting complex compound is said to be labile. Here, half-life period may be of the order of 10 to the power minus 2 seconds or less. Half-life period of the reaction, first order, the half-life period will be around 10 to the power minus 2 seconds. If it is 10 to the power minus 2 seconds, then the reaction can be followed with stop. If it is less than minus 2 seconds, then NMR other techniques are to be used. So fast reactions, labile complex studies can be done with the help of stop flow technique. Example, an example of labile complex. So if you have this complex ion, AgNH3 hold 2Cl. This is diamine silver 1 chloride. The oxidation state of silver is 1. Diamine silver 1 chloride or tolerance reagent. This is called tolerance reagent. How this is prepared? So if you have silver chloride, white precipitate, to that if you go on adding ammonia, then this complex, this is colorless. This complex is colorless. To this, if you add dilute hydrochloric acid solution, to this complex, if you add dilute hydrochloric acid solution, immediately you will get silver chloride white precipitate plus ammonium ion will be formed, and chloride ion will be there in the medium. So this is colorless and the product is white. To the tolerance reagent, if you add dilute hydrochloric acid solution, then you get immediate white precipitate. That means the silver ammonia bond is breaking, silver bond, ammonia bond is breaking very quickly. Why this is breaking very quickly? Because when you add acid, ammonia has strong affinity for acid, producing ammonia. Ammonia has very strong affinity for H plus ion, producing ammonia. The pK of Na prime will be 10 to the power plus 9. pK of ammonia 1 is around 9. So dissociation constant is 10 to the power minus 9. So association constant will be 10 to the power plus 9. Therefore, ammonia has very strong affinity for H plus. So therefore, it leaves silver ion. So if you compare silver ion ammonia bond and ammonia and H plus bond, this bond will be stronger in comparison to this bond. Therefore, ammonia leaves silver ion. As a result, silver chloride gets precipitated. Why silver chloride gets precipitated? Because Kst, solubility product of silver chloride is 10 to the power minus 10. At 25 degrees, solubility product is very low. Therefore, immediately silver chloride will be getting precipitated. Similarly, there is another example. If you take copper sulfate solution, to that if you go on adding dilute ammonia, you will get a deep blue copper complex. This can be done, this experiment can be done in any laboratory. So, Cu NH3 whole for 2 plus. This is a tetramine cupric ion. This complex is tetramine cupric ion. This is deep blue. This experiment is very simple. It can be done in any laboratory. You take copper sulfate solution. To that, you go on adding ammonia. Immediately, you get a bluish white precipitate of cupric hydroxide. Then the precipitate will dissolve in excess ammonia, producing tetramine copper ion. This is deep blue. To this, if you add few drops of concentrated sulfuric acid, then immediately you get this is hand blue. The deep blue color will vanish, producing a faint blue hexaqua cupric ion. Here also, copper ammonia bond breaking is breaking very fast. Therefore, the initial complex is lower. So remember this: if the metal ligand bond breaks quickly, then the complex will be live. If the metal ligand bond does not break quickly, then the complex will be inert.
ପିଲାମାନେ ଶୁଭୁଛି? ବ୍ଲର୍ ଆସୁଛି?
କ'ଣ ଆଡ଼ଜଷ୍ଟମେଣ୍ଟ ଟିକେ କରିଦିଅ
ଦେଖି अभी देख पढ़ो अभी कौन लिखा है
अगर क्लियर है
निकाल इनर्ट कॉम्प्लेक्स if the metal ligand bond does not break quickly or it takes few minutes to break, the metal ligand bond starting complex. Is said to be inert. If the metal ligand bond does not break quickly, or it takes few minutes, it takes few minutes to break metal ligand bond, then the starting complex is said to be inert. Inert means the complex compound will not react easily. Labile means when the complex compound reacts easily, then the complex will be labile. If the complex compound does not react quickly, then the complex is labile. The substitution reactions of inert complex can be studied with the help of spectrophotometer or pH-metry. The reactions can be followed spectrophotometrically easily. So, example, let us take some examples. So, this complex this is orange yellow in color. This complex, Werner prepared this complex. Here the oxidation state of cobalt is +3. Werner prepared this hexamine cobalt 3 chloride. This complex is hexamine cobalt 3 chloride. This complex is orange yellow. To this complex, even if you add concentrated hydrochloric acid, the reaction does not take place. The complex is stable and it does not react with concentrated hydrochloric acid solution. Because when concentrated hydrochloric acid is given, the ammonia could have reacted with hydrogen ion and the aqua complex could have been produced. But this complex does not react with concentrated hydrochloric acid, therefore the complex is inert. The complex, therefore, hence the complex is inert. Let us take example of another complex. So most of you are aware with this complex. Potassium hexacyanoferrate, ferrate 2. Potassium hexacyanoferrate 2 or potassium ferrocyanide. This complex is yellow in color. Yellow in color and it is stable. And this complex is highly kinetically stable. This complex is highly kinetically stable, does not react easily. Therefore, does not react easily means iron cyanide bond does not break easily. That means iron 2 cyanide bond does not break easily. Therefore, the ferricyanide is stable. Iron 2 cyanide bond does not break easily. Therefore, this complex will be inert. These two complexes are inert.
No, sir.
bond theory explanation. Valence bond theory explanation of lability and inertness. You must be aware of valence bond theory. What are the postulates of valence bond theory? First postulate is each metal atom or ion will make available number of orbitals equal to its coordination number. These vacant orbitals will be hybridized so that the complex compound gets a shape. Metal ligand bond formation takes place by the overlap of vacant hybrid orbital of the metal ion and filled sigma bonding orbital of the ligand. What is sigma bonding orbital? Suppose you take chloride ion, the valence electron 3px2, 3py2, 3pz2. If sigma bond takes place, bond formation takes place around z axis, then these two electrons are sigma bonding electrons. Suppose you have ammonia. Ammonia, this lone pair of electrons is nothing but filled sp3. Ammonia, the hybridization is sp3, therefore these two electrons will be present in sp3 orbital. So this is ammonia has filled sp3 orbital. So these are sigma bonding orbital of ligand. Suppose we take a complex like this, cobalt 3. Cobalt 3 is a D6 system. So 1, 2, 3, 4, 5, 6. So 3D, 4S, 4P, 6 electrons will remain like this. Six electrons will remain like this. D orbital, these 6 electrons will remain in the D orbital like this. So this is 3dxy, 3dyz, zx, dz square, dx square minus y square. So for this complex, the coordination number of metal is 6. Coordination number of cobalt 3 is 6. So 6 vacant orbitals are needed. So these 6 electrons will be accommodated can be accommodated like this. 1, 2, 3, 4, 5, 6. So this is 3dxy, yz, zx, z square, dx square minus y square, 4s, 4. So 6 electrons will be accommodated in 3 d orbital, dxy, dyz, dzx orbital. 6 electrons are accommodated here. Then d2sp3 orbital, d2sp3 hybridization is taking place. d2sp3 hybridization will take place, producing inner orbital complex. When 3d orbital will be used, that will produce inner orbital complex. If the 4d orbitals are used, then that will produce outer orbital complex. So inner orbital complex is produced. Now so these are vacant D2sp3 orbitals. So ammonia filled sp3 orbital. This is filled sp3 orbital. Filled sp3 orbital ammonia can overlap with vacant D2sp3 orbital producing cobalt 3 ammonia sigma bond. So cobalt 3 ammonia sigma bond is produced by the overlap of vacant D2sp3 orbital of cobalt and filled sp3 orbital of ammonia. Now here for this system there is no vacant d orbital. There is no vacant d orbital. Only vacant outer d orbitals are possible. Vacant outer d orbital will produce less stable complex. So therefore, inner orbital complexes will be mostly. If there is no vacant d orbital, then the inner orbital complex will be inner. They will be mostly inner. If the d pi orbital, these are called d pi orbital. D pi orbitals are filled, completely filled. If d pi orbitals are completely filled, then such complexes will be inner. If we consider F6 3 minus. This is hexafluoroferrate free. So this is a outer d orbital complex. Why? How to say this is outer d orbital complex? Because this is d pi. Iron free means d pi. So 1, 2, 3, 4, 5. So sp3d2 hybridization takes place. sp3d2 hybridization takes place, leading to formation of outer d orbital complex. Outer orbital complex. Or this is high speed. Outer orbital complexes are high speed, inner orbital complexes are low speed. Because here 3D orbitals will contain 5 unpredictable. From the magnetic moment study, you can say whether the complex is outer orbital or inner orbital complex. The previous complex was diamagnetic, and this complex will be paramagnetic. The spin of the magnetic moment is equal to n into n plus 2 Bm. Bohr magneton. N is number of unpredictable. So this will be 5 into 7. So root over 35 Bm. So spin only magnetic moment will be root over 35 Bm. For this complex, so this is outer orbital complex. When these 4d orbitals are used, energy of the 4d orbitals will be higher in comparison to 3d orbitals. So here, in the spin system, metal ligand bond will be slightly larger. Therefore, such complexes will be inert. As a labile, such complexes will be labile. So outer orbital complexes will be mostly labile, and inner orbital complexes will be mostly inert. So valence bond, what does it explain? It explains that inner orbital complexes will be mostly inner, provided d pi orbitals are completely free. high speed will be mostly labile. D0, D1 and D2 systems will be labile. D0, D1, D2 system, what does it mean? What does it mean? D0, D1, D2 system is, suppose D0, 1, 2, 3, 4, 5. So this is 4P, 4S, 3D. So here the d orbitals are vacant. Therefore, any ligand can enter this in associative mechanism. In associative mechanism, the metal ligand bond formation will be easier because these d orbitals are vacant for D0 system. And for D1 system, D1 system means only one electron is there. So this system also there are two d orbitals vacant. Therefore, again metal ligand bond formation is easier in associative mechanism. In a D2 system, also there is one vacant d orbital. This is dxy, dyz, dzx. One vacant d orbital is there. So therefore, metal ligand bond formation is possible. So therefore, in the associative mechanism, so D0, D1, D2 system will be mostly labile, and inner orbital complexes will be inert provided 3 pi orbitals are completely filled up, and outer orbital complexes, high spin complex will be mostly labile, and D0, D1, D2 systems will be mostly labile. So valence bond theory could roughly explain the lability of complex compounds, but it does not focus any light on other systems. It only says D0, D1, D2. What about D3, D4, D5, D6, D7, D8, D9 and D10 systems? These systems, why? These systems, some of these systems will be labile and some of these systems will be inert. The correct explanation is not provided by valence bond theory. Therefore, crystal field theory only can easily say which systems will be labile and which systems will be inert.
d pi orbitals ಕೂಡ ಕೂಡ d pi orbitals बोले
d pi वाला ना
हां सर d pi orbitals
d pi वाले माने pi बॉन्ड करन ए ऑर्बिटल गुडा ऑक्टाहेड्रल कॉम्प्लेक्स रे dxy dyz dzx these orbitals can form pi bond within. So therefore these are called d pi orbitals. Sigma bond रे कोड यूज होची dz square and d x square minus square. These are sigma bonding. Metal and sigma bonding orbital एडा होची pi bonding. दरपले दरपले माने pi bonding यूज होती माने octahedral. Tetrahedral उल्टा है. एगुडा pi bonding हो एटा sigma. octahedral ले these are d pi orbital. माने ligand रो suitable एडा field अछि ता. Ligand रो vacant orbital संगे माने pi bond करबे. सेम गुड एग्जांपल, let us take one example. Suppose you take this complex. So this is a D6 system. The oxidation state of iron is +2. So D6 system. So So this D6 system will have field dxy, dyz and dzx orbitals. Field it is the तो cyanide कार्बन रो जो वैकेंट p ऑर्बिटल थियो से वैकेंट p ऑर्बिटल या से पाई बॉन्ड फॉर्मेशन करे बुझो जदी गोटे मेटल लिगैंड सिग्मा बॉन्ड फॉर्मेशन होला मेटल लिगैंड सिग्मा बॉन्ड केमती फॉर्मेशन होला हाइब्रिड ऑर्बिटल ऑफ द मेटल विल ओवरलैप विथ वैकेंट hybrid orbital of the metal is overlapping with field sigma bonding orbital of the ligand. But suppose this is your z axis. This is the z axis, and this is x axis. So if this is dzx, this is field dzx. So field dzx can overlap with vacant x orbital px, vacant px orbital of the ligand of the pi. What will you know? The vacant hybrid orbital of the metal will overlap with field sigma bonding orbital of the ligand
to form the sigma bond.
Ligand metal sigma bond. And field d pi, these are field d pi. So field d pi orbital of the metal can overlap with vacant px orbital of the ligand, producing a pi bond. So what does it will look like this? This is sigma bond, this is pi. Clear or not? Sigma, how sigma bond is formed? When hybrid orbital of the metal ion vacant hybrid orbital of the metal ion overlaps with field sigma bonding orbital of the ligand. Sigma bond formation आएगा. Similarly, field d pi orbital of the metal will overlap with field p pi or d pi. It may be p pi or d pi. Vacant. Phosphorus ligand है ना TRP है ना. TRP यदि use करता हो, इट field d ये vacant d pi.
ओहो.
Phosphorus थिले एटी vacant d pi हो. जदि एटी halide अच्छी, ओटा halide अच्छी, तो सेठी हो field ये vacant अन्य कार्बन सिस्टम अच्छी. कार्बन सिस्टम हो vacant p pi हो. कार्बन सिस्टम जेमता ligand अच्छी vacant p pi अच्छी. किंतु यदि phosphorus ही था ना, एटी vacant d pi था. Phosphorus है d orbital vacant.
हाँ.
So vacant d pi, यार d pi सारा pi bond करो. So pi bond is formed either field d pi of metal plus vacant p pi of ligand. ये वाला pi bond है. How can pi bond हो? Field d pi of the metal plus vacant
d pi
of
of ligand.
Then the trialkyl phosphine is vacant d pi orbital. Carbon monoxide, यदि हमें carbon monoxide नवा, ऐसे रहेगा vacant d pi orbital.
ट्राइअल्काइल फॉस्फेन रे हमरो p ऑर्बिटल भी तो वैकेंट रहू सर. काई ना तार तो sp3 हाइब्रिडेशन हबो.
sp3 आ गोटा p sp3 रे फील्ड अछि. फील्ड देबे ना. sp3 ऑर्बिटल जो रहला
अमोनिया रे फॉस्फेन रो.
हां कोन दिया
सर. अच्छा. तेनो सेठी फास्फोरस रो d ऑर्बिटल रे रिसीव करिवो इलेक्ट्रॉन माने ओवरलैपिंग करिवो.
इलेक्ट्रॉन रिसीव करिवो मेटल ओवरलैप करिवो तो
ओवरलैप करिवो d ऑर्बिटल रो. अच्छा आउटरे भी ए जोटा कहले आउटरे के खाली कह दे ए जो
हां करो
वीपीटी रो आउट के टिक कर. हां
कॉन्ग्रेचुलेशन.
ठीक है. अच्छा.
आउटर डी ऑर्बिटल है कौन 4d रे एनर्जी बेसी 3d और 4d रे कार एनर्जी बेसी हो
जेते पाखु को आसीबो ऑर्बिटलटा न्यूक्लियस रो
सेटा क्वांटम नंबर यदि बढ़िबो
आज्ञा
एनर्जी बढ़िबो
आज्ञा
3d रे प्रिंसिपल क्वांटम नंबर केते
3 सेठी 4 रे अधिक हो
अधिक सेटा जतडा एनर्जी ऑर्बिटल बढ़िबो से मेटल लिगेंड बॉन्ड लॉन्ग साइज बढ़िबो ना दूसरा बुझो उनका 3d d2 sp ये हैबिट ऑर्बिटल का जो साइज वाला काटी जो साइज है ఎంత ఉంది దాంట్లో sp3 4d
বড়
বড়াই তাহলে এটি মেটাল লিগ্যান্ড বন্ড সাটার হবে এটি মেটাল লিগ্যান্ড বন্ড লম্বা তাহলে এটি লবাই লাগে বুঝ পারলেন আউটার ডি অর্বিটাল ইউজ করতাম
বড় হইব বন্ডটা মানে উইকার হই গলা
উকরণ লবাই
লাবাই
The outer d orbital complexes are
मोस्टली लबाई
mostly level. Inner d orbital complex, inner orbital complexes will be inner. Generally inner.
हां मैंने पहले के क्वेश्चन पचारि पचार अभी जी पढ़ा है इनर्टनेस और लाबिलिटी भितर जहाँ अच्छी मनरे क्वेश्चन पचार सोमवार तो सर अगर खुली क्लास हो आर वीक फिजिकल क्लास हो पारिबो
ये नोटा आज पूरा जेरस कर दो
आगे सर
जेरस कर दे कि फोटो उठा के जेरस कर दला इनाम दे दो
हाँ
इला पचर
50
चिल्लेट सर चिल्लेशन इफेक्ट लाबाइल इनर्टनेस पर किसी इफेक्ट पका कि चिल्लेट इफेक्ट
चिल्लेट एंड इनर्ट जनरल है चिल्लेट्स आर मोस्टली इनर्ट बिकॉज़ स्टेबिलिटी बढ़ी हो
चिल्लेशन होबा द्वारा स्टेबिलिटी इंक्रीज होची तंतर इनर्टनेस बढ़ी जाउची
मेटल लिगेंड बॉन्ड इजीली ब्रेक करियोनी चिल्लेट किंतु I mean lability जेतले कहूचे that is mostly kinetics. When you talk of lability, you are talking of kinetics. You are not talking of thermodynamic stability. So kinetics जो rate constant बेसी हो से system labile हो जो rate constant कम हो तो system inert हो खाली किलेट कह देले तो खाली labile हो नहीं को system तुम नो तो को d और d system टा कौन अछि d10 system labile d10 system वाले labile है किलेट हो कि ना हो
D10 टे काई सर तो लाबाई हबो
हां
D10
रखा D10 रे इनर ऑर्बिटल कॉम्प्लेक्स है पारे अपना आउटर ऑर्बिटल
करेक्ट
D10 जब सिस्टम रे गलो इनर ऑर्बिटल है पारे
आउटर ऑर्बिटल हबो
आउटर ऑर्बिटल वाला पाइला
करेक्ट
D10 सिस्टम मतलब माने कोन D10 वाला 1 2 3 4 5 1 2 3 4 3D, 4S, 4. Return system is G. Return system is G system. Already sp3d2 hybridization. Data is outer orbital complex. And the D5 high speed. D5 system for iron system. Iron 3 is D5 high speed.
FEF6.
FEF6. Hexa 4 Farad 3. D5 है किंतु मैग्नेटिक मोमेंट रो जणा पड़ती जे पांचटा डी ऑर्बिटल कंप्लीटली गोटे गोटे इलेक्ट्रॉन अछि मैग्नेटिक मोमेंट जणा पड़ता से आउटर डी ऑर्बिटल भी जो आउटर डी ऑर्बिटल है लेवल है करेक्ट सो इनर डी ऑर्बिटल कॉम्प्लेक्स आर मोस्टली इनर्ट एंड आउटर डी ऑर्बिटल कॉम्प्लेक्स आर मोस्टली labile मतलब इटा D0 D1 D2 सिस्टम का अर्थर एक्सपेरिमेंट तो D0 सिस्टम मनकर scandium 3 plus. Scandium 3 plus is D0 system. There is no electron in D orbital. Suppose you take a scandium 3 complex and there are 6 ligands. So hybridization will be D2sp3. So inner D orbital complexes will be produced. But here the inner D orbital complexes produced hele madhyam eta labile hai. Why it will be labile? Because if the mechanism is associative, then the system will be labile. Associative ka labile because here d orbitals are vacant. So ligand can form a bond with the vacant d orbital. Suppose your complex is like Ml. You are giving another ligand L1. So L prime. This type of intermediate or transition state is possible, easily possible. Because this complex has a vacant d orbital, so the L prime ligand can form a bond with the vacant d orbital, producing a intermediate or transition state where the coordination number of the metal will increase. Similarly, you come to D1 system. So if you have D1 system, then there are 2 d orbitals are vacant. Similar situation is possible. For D2, similar situation is possible. For D3 will be inert. Yes. D1 रहेगा, D3 रहेगा, सब डी गोटे गोटे इलेक्ट्रॉन रहेगा, so inert. कुछ पढ़ा? So this is valence bond explanation of lability and inertness. Now we will consider the exchange reactions. Exchange reaction rate constants, that is called K exchange, first order rate constant. Unit is second inverse. Exchange reaction rate constant is second inverse. What is exchange reaction? Suppose we take metal is coordinated to water molecule. To this coordinated water, you have to add a water containing labeled oxygen. That means you are adding. Then what is the product? Product is so here the concentration is, suppose here concentration is 55.5 molar. Water concentration is 55.5 molar. So rate will depend on the concentration of the complex amount. Here this rate constant is called K exchange. This rate constant is called exchange rate constant. So if the metal ligand bond is longer, then the exchange rate constant will be high. It will easily break. So if the metal water complex is labile, K exchange will be high. High value of rate constant. If the metal water bond complex is inert, K exchange will be low. For example, let us take one example.
Labeled hydrogen oxygen, it is oxygen ro 18 isotope ta use kara.
Oxygen 18. This is oxygen 18.
Radioactive isotope.
Oxygen 18 water. So एटी वाटर एटी सब्स्टिट्यूट करूँ जदि एटी मेटल लिगैंड बॉन्डटा स्ट्रांग हो ताले सब्स्टिट्यूशन रेटटा कम हो जदि क्विकली ब्रेक करिया ताले एटी ऑक्सीजन इजीली सब्स्टिट्यूट हेइयो ए ऑक्सीजन सब्स्टिट्यूट हेइयो ताले एटी एक्सचेंज रेट कांस्टेंट बढ़ी जिवो क्विकली रिप्लेसमेंट होला रेट कांस्टेंट बेसी हो जदि स्लोली रिप्लेस होला तो रेट कांस्टेंट कम गोटे एग्जांपल मु तुम क्लियर exchange rate constant का बड़ा example. You take this complex. So this is a D4 system. Here the rate constant, exchange rate constant is greater than 10 to the power 8 second inverse. Now the D3 system. So the exchange rate constant approximately equal to 2.4 into 10 to the power minus 6 second inverse. So let us compare these two systems. If you compare these two systems, the D4 system, this is a D3 system. This is a D4 system, this is a D3 system. So if it is D4 system and here the exchange rate constant is 10 to the power 8, greater than 10 to the power 8, here the exchange rate constant is 10 to the power minus 6. Then where the rate is slower? So here the rate is slower. Therefore, this complex is labile and this complex will be inert. So if the exchange rate constant is high, then the complex becomes labile. If the exchange rate constant is low, then the complex is inert. Is that clear? Then why here the exchange rate constant is high, here the exchange rate constant is low? Why? Because this is a D4 high spin system. This complex is high spin. D4 high spin. Then what is the electron distribution? Electron distribution will be E2G3 EG1. So for high spin complex, the electron distribution will be T2G3 EG1. So if EG orbital is unsymmetrically filled up, then there will be strong Jahn-Taylor distortion. Strong Jahn-Taylor distortion will come theta axial bond longer is. So what is happening here? Chromium 2 so this is Z out distortion. Z out distortion. If the bond along Z axis is longer, then that is called Z out distortion. In which situation Z out distortion is possible? If EG means dz square and dx square minus 1 square. If the dz square orbital contains one electron, Then here there is no electron here, so this will be Z out distance, Z axis. The ligand will face more electron. Z axis रे ligand टा बेसी repulsion face करियो काहे कि Z dz square electron अछि, so Z axis रे repulsion बेसी face करियो. बेसी face करा द्वारा कोन हो Z axis टा longer है. X axis y axis रे face करियो नाही काहे कि d x square minus y square orbital vacant अछि. So से x axis y axis रे फेस करियो नाही. जदि एटा इलेक्ट्रॉन टा d x स्क्वायर माइनस y स्क्वायर हो सेटा z in डिस्टॉर्शन है. z out z in एटा पढाबो हमर जॉइंट डिस्टॉर्शन पढाबो. बट हियर इन chromium complex joint distortion is not possible. What is joint distortion? If Eg orbital is unsymmetrical for tetrahedral octahedral complex, if Eg orbital is unsymmetrically filled up, then only there will be joint distortion. So D9 system there will be joint distortion, D4 system high speed there will be joint distortion. For here no joint distortion is possible because this is D3, so T2G3 Eg0. So D3 means T2G3 Eg0, so no joint distortion. So here chromium 3. So here the complex will look like this, no joint distortion. So there is no Z in or Z out distortion. Z out or Z in. So Z out हेतले x axis y axis रे बॉन्ड longer ही था. Z in Z out हेले x Z axis रे बॉन्ड longer ही हो. Z in हेले shorter ही. So here there is no Z in Z out distortion. So here the exchange rate constant is 10 to the power -6. Here the exchange rate constant is 10 to the power 8. So the higher is the exchange rate constant, higher will be the lability. What is the conclusion? Higher is the exchange rate constant, higher will be lability. Then what are the factors which controlling the lability? Why high spin complexes are more labile in compared to low spin complexes? This fact will explain.
एक्साक्ट क्रोमियम रे सर जो D4 सिस्टम रहउची हमरो D4 रु हमरो D रु एटा होछ सर आउटर ऑर्बिटल कॉम्प्लेक्स होछ ना इनर ऑर्बिटल होछ ता आउटर ऑर्बिटल होछ माने D4 टा भीतर सेम रहि जाउची 1 1 1 1. अच्छा सेठी जो स्ट्रक्चर टा होची सेठी जो D ऑर्बिटल यूज करा है सेटा आउटर D ऑर्बिटल टा सब यूज करा है
कोन रे
जो हमरो एक्साक्ट क्रोमियम रे
हाँ इटा इनर ना इटर आउट D4 आउटर एथरे इनर.
ओहो एठी माने सेटा को हम बुझछ
सेटा
आउटर
एटा आउटर हो ना D4 पर अनपढ़ इलेक्ट्रॉन चारटा रहे चारटा अनपढ़ इलेक्ट्रॉन आउटर हेले भी हमर जो Z in Z out होछि सर सेटा इनर रे होछि ना आउटर रे नै Z in Z out कोन जे इलेक्ट्रॉन टा इची रे रहिला सेटा दीटा संभावना अछि. dz स्क्वायर होय पारिबो नले dx स्क्वायर माइनस y स्क्वायर होय कोनटा बुझो दीटा संभावना अछि. जदि dz स्क्वायर रहिला इलेक्ट्रॉन टा तले एक्सियल बॉन्ड टा लॉन्गर है. जदि x स्क्वायर माइनस y स्क्वायर रहिला तले x एक्सिस और y एक्सिस बॉन्ड टा लॉन्गर हबो इन कंपेयर टू z एक्सिस. ऑप्शन कोन देखा जदि Z in होगा ना बेटे एमटीएम देला मतलब dz स्क्वायर वैकेंट d x स्क्वायर माइनस y स्क्वायर गोटे इलेक्ट्रॉन. तो एठी कोन आइबो ए बॉन्ड टा लंगर है ना x एक्सिस एटा ना y एक्सिस एटा ना z एक्सिस यदि x स्क्वायर माइनस y स्क्वायर इलेक्ट्रॉन रहला तो xy प्लेन रे जो वाटर टा आसुची बेसी रिपल्सन फेस करी तले कोन हो ए x एक्सिस ए बॉन्डटा लंबर है इन कंपेयर टू मेटल वाटर बॉन्ड एलम z एक्सिस से मध्यर मन लेवल सेत्रे भी लेवल एटा हो z इज कॉल्ड z इन डिस्टर्शन एटा सब पढ़ा हो जानटर डिस्टर्शन पढ़ा z इन डिस्टर्शन इज कॉल्ड z इन डिस्टर्शन Higher is the ionic radii of the metal ion, more easily the metal ligand bond will break. Higher is the ionic radii of the metal ion, more easily the metal ligand bond will break, and the system will be level. Lower is the ionic radii of the metal ion, the metal ligand bond does not break. The system will be enough. Very very important point batan discuss kara hoche taka. Higher is the ionic radii of the metal ion, more easily the metal ligand bond will break and the system will be level. Lower is the ionic radii of the metal ion, the metal ligand bond does not break easily, the system will be enough. जिते स्मॉलर है जो मेटल लिगैंड बॉन्ड सिस्टम ला सते इनर्ट जिते लॉन्गर है जो मेटल लिगैंड बॉन्ड सते सिस्टम गण लंबा for the same oxidation state, same coordination number, R high spin will be greater than R low spin. Coordination number fix ଅଛି ଗୋଟେ ମେଟଲାନ୍ ର coordination number fix ଅଛି ତାର ହାଇ ସ୍ପିନ୍ ରେଡିୟସ୍ ଟା लो ସ୍ପିନ୍ ରେଡିୟସ୍ ଅପେକ୍ଷା ବେଶୀ ହେବ କାହିଁକି ବେଶୀ ହେବ ହାଇ ସ୍ପିନ୍ ସିଷ୍ଟମ ମିନ୍ସ ଇଜି ରେ ଇଲେକ୍ଟ୍ରନ୍ ରହୁଛି ଇଜି ରେ ଯଦି ଇଲେକ୍ଟ୍ରନ୍ ରହିଲା ସେଠି ମେଟାଲ ଲିଗାଣ୍ଡ ରିପଲ୍ସନ୍ ବଢିଯିବ ହିୟର मोर metal ligand repulsion, here less metal ligand repulsion. एटी इजी रे इलेक्ट्रॉन रहबा एटी हाई स्पीड मान इजी रे इलेक्ट्रॉन रहबा इजी रे इलेक्ट्रॉन रहबा हाई स्पीड मान कोन d4 मान करे d4 हाई स्पीड एले कोन रहबा t2g3 eg1 d4 लो t2g3 for eg0. So compare this and this. Here the ligand, here the electron is in eg orbital. So because the ligands are approaching the metal ion along x-axis, y-axis and z-axis, here repulsion between metal ion electron and ligand electron will be more. Here repulsion between metal electron and ligand electron will be less. So metal ligand bond will be longer here, metal ligand bond will be shorter here. So K exchange here will be high, K exchange will be low. Now for high spin complex, EG orbitals are filled, mostly EG orbitals are filled. Because high spin only you can compare D4 to D4, D5, D6 and D7. Only these 4 systems you can have either high spin or low spin. So in high spin situation, this will be T2G3, EG1. In low spin situation, this is T2G4, EG0. So here it will be T2G3, EG2. Here will be T2G5, EG0. So here it will be T2G6, T2G4, EG2. Here will be T2G6, EG0. Here D7 system will be T2G5, EG2. This will be T2G6, EG1. So look at these two, D4, D5, D6, D7. Here the EG orbital has 1 electron, here the EG orbital has no electron. So here metal ligand repulsion will be more, here metal ligand repulsion will be less. D5 system, here EG orbital has 2 electron, here EG orbital has no electron. So metal ligand repulsion will be more here in comparison to this. Here also more in comparison to this. Here T2G orbital has 2, EG orbital has 2 electrons, here 1 electron. So here repulsion will be more, here repulsion will be less. So therefore, radius high speed will always be for the same coordination number. For the same coordination number, radius high speed will be greater than radius low speed. Therefore, high speed complexes will be more, metal ligand bond will be longer, so they will be labile, mostly labile, they will be mostly inert. So let us take some examples. So now we are comparing D4, D5, D6 and D7 system. So these are all high spin complexes. These are all complex are high spin. All are high spin complex because the EG orbitals are, you look at, this is the electronic configuration for high spin complexes. Now here what we see, the ionic radii here is 0.94, here 0.97, here 0.92, here from 0.97 to 0.89, the ionic radii is decreasing. So if the ionic radii is decreasing, the rate K exchange should decrease. When the ionic radii is decreasing, the exchange rate constant should decrease. This is the exchange rate constant is the highest here, exchange rate constant is the lowest here. But why there is exception here? The exception is Jahn-Turner distortion. Here Jahn-Turner distortion is possible. On all these three cases, Jahn-Turner distortion is not possible. Due to Jahn-Turner distortion, the axial bonds are becoming longer and therefore the exchange rate constant is high. So in this way we explain D4, D5, D6, D7 system, all high spin system. Now remember one thing, if the electron enters T2G, there will be contraction in ionic side. If the electron enters EG, there will be elongation in ionic side. So, if the electron enters T2G orbital, there will be contraction in ionic side in comparison to the previous or earlier metal. If the electron enters EG orbital, there will be elongation in ionic side in comparison to the earlier metal. So let us explain this. This is a very, very important point because on this, if you understand this point, then you can explain many thermodynamic properties like lattice energy, heat of solvation, heat of hydration, etc. You can explain. So we will consider D0, let us be D1, D0, T2G0, EG0, D1, high spin. We are considering all high spin situation. T2G1, EG0, D2, T2G2, EG0, D3, T2G3, EG0. So, from D0 to D1, the electron is entering T2G. So, there will be contraction in ionic side. So, up to this, of D3 system, there will be contraction in ionic side. Because the electron is entering P2G level. Electron is entering P2G level. So there will be contraction in next side. So if you take D4, now we are considering only high spin situation. It will be T2G3, EG1, D5, T2G3, EG2. So from here to here, because now the electron is entering EG level, so size will now increase. So elongation in next side. So D5, D6, D6 means T2G4, EG2, D7, T2G5, EG2, D8, T2G6. Now from here D5 to D6, the electron is again entering T2G level. So there will again contraction. Contraction in this side. Then D9, T2G6, EG3, D10, T2G6. So here EG4. Again elongation in next side. So first there will be contraction, then elongation, then contraction, then elongation. So if you look at the plot,
sir, it is subject to high spin inner
high
orbital.
spin, all outer orbital,
Outer
high spin means outer. High spin means outer orbital. So look at what is happening, look at the plot. Net getter ಕೊಡ್ತೀವಿ exchange reaction net getter. ಈಗ plot ಅಲ್ಲ very interesting plot. Calcium, scandium, titanium, vanadium, that's the probability. Chromium, then manganese, iron, cobalt, nickel, copper, so this is D0, D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. Octahedral ionic radii in Armstrong. Octahedral ionic radii means all these complexes are forming hexaqua. These complexes are all hexaqua complexes. That means the complex is M L2/6 2 plus. 0.6, 0.7, 0.8, 0.9, 1 angstrom. 0.6, 0.7, 0.8, 0.9, 1. Titanium. Vanadium 0.7. So I told you that from D0 to D3 there will be contraction in ionic site. D0, this is D0 to D3. There is contraction in ionic site. From D0 to D3 there is contraction in ionic site. Then from D4 D5 there will be elongation in ionic site. So D4 D5. So chromium is D4. Then manganese is 0.8. From chromium is D4 to D5, there is again elongation in ionic site. So up to D3 there is contraction in ionic site. Then this is elongation in ionic site. Then from D6 to D8 again there is contraction in ionic site. So nickel is your 0.65. And copper, zinc, there is again. So here from D0 to D3 there is contraction in ionic site. Why there is contraction? One way as the electron is being filled up, the number of electrons is increased. Then there should not be any contraction. But the nuclear charge is also increasing. Here the nuclear charge for calcium ion, the proton number is 20. For scandium 2, the proton number is 21. So proton number is increasing. Proton number is increasing. So screening effect of T2G level is less in comparison to EG level. So therefore, when the electron is entering T2G level, the repulsion due to screening effect is not high, but the proton number is increasing. Therefore, electron cloud are squeezed. So therefore, what this plot indicates? From D0 to D3, there is contraction in ionic site. So therefore, the exchange rate constant will decrease. From here, vanadium to manganese, the exchange rate constant will again increase. From manganese to nickel, exchange rate constant will decrease, then it will increase. So ionic radii is related to lability and inertness of the metal sector also. Now let us look at the data. Then we will explain what is the experimental data of inertness and lability. तो बहुत बड़ी
हाँ सर
ये जो डाटा जेडीली रु दिया है बहुत जिनस फिजिकल प्रॉपर्टी एक्सप्लेन कर जेडीली अच्छे तो C JD for this plot. Serial number LNMS2 electron beam into the ion KXN
Second and last.
ନା ଦେଖାଉଛି ଏପଟେ ଏପଟେ ଦେଖାଉଛି ଏପଟେ ଦେଖାଉଛି
अच्छा एल बोली कौन लाता ना इधर
LN means ligand
फुल
LN A वाला बेटा LN means N number of ligands
गोटी वाटर अच्छी
हाँ वाटर इटा एल भी वाटर है
वाटर
एटा डिपेंड करेगा 5 है पर वाटर है 5 हो 5 plus 1 6 so let us consider this complex Cr H2O all 6 2 plus this is D4 ionic radii high speed 0.94 T2 G3 Eg1 Jahn-Teller distortion greater than 10 to the power 8. D3 0.76 manganese D5 the antenna distortion. So these are the data I have written for the K exchange can be explained on the basis of the ionic radii is shown here. So from manganese to nickel, the ionic size is decreasing. Therefore, the rate constant should decrease. From manganese, you see from manganese here the rate constant is 2.1 to 10 per 7, and for nickel it is 3.2 to 10 per 4. 3.2 to 10 bar from manganese to nickel. From manganese to nickel, the ionic radii is decreasing. From manganese to nickel, the ionic radii is decreasing. Therefore, the lability should decrease. So manganese should be most labile and nickel should be least labile. So therefore, the rate constant is decreasing from 2.1 to 2.4, 1000 times. 10 to the power 3 means 1000 times it is decreased. Now another in copper and zinc there is again increase. From copper to zinc there is increase in exchange rate constant. Now here there is again increase in ionic radii. So increase in ionic radii means increase in exchange rate constant. So lability is again increasing. And here what about copper? In copper the electron copper 2 means D9, it will be T2G6 Eg3. So when Eg orbital is unsymmetrically filled up, there will be strong distortion. So this is Z out distortion. In copper complexes there is always Z out distortion because dz square level will have 2 electrons and dx square minus y square orbital will have 1 electron. So there will be strong Z out distortion. So copper zinc again, the ionic radii is increasing. Therefore, the lability should increase. So here the lability is increasing. There is another factor. If you take a same system, it is a D5 system. This is D5 system, but this complex is more labile. You see, compare this and this. 1000 times the hydroxo complex is more labile in comparison to the non-hydroxo complex. Why this is happening? We compare these two complexes. One is hydroxo, penta-aqua hydroxo. One is penta-aqua hydroxo. Iron hydroxo complex. This is penta-aqua. This complex is penta-aqua hydroxo iron system. D5. D5. The exchange rate constant is of the order of 1.2 into 10 to the power 5. 1.2 into 10 to the power 5. Why this is happening? But whereas if you take a same complex, but all the water molecules, no hydroxo system. So if you compare basic nature, hydroxide is more basic than water. Hydroxide is much more basic than water. So if one water is lost, so there will be vacant vacant D2sp3 orbital. If one water is lost, there will be vacant D2sp3 orbital. The vacant D2sp3 orbital can form, this is filled p orbital, filled 2p orbital, can form pi 1. Vacant D2sp3 orbital of iron 3, this is iron 3, can form pi 1 with the filled 2p orbital of oxygen. Therefore, the intermediate will be stabilized. Therefore, the complex will easily form the intermediate. Therefore, lability will increase. Therefore, here the rate constant is 1.2 into 10 power 5, and here the rate constant is 1.6 into 10 power. Here the exchange rate constant is 1.6 into 10 power 2. Here the rate constant is low, here the rate constant is high. So this complex will be more labile than this complex because the hydroxide is more basic than water. So electron pushing, this will easily push electron to the iron 3 center. So the water molecule should escape, leading to formation of square pyramid intermediate, which will be stabilized by pi 1. Here, the basic nature of this is less, and also pi bonding of water molecule is not reported. So pi bonding due to water molecule, although these are filled p orbital, but pi bonding is not reported for water molecule. Therefore, all systems, hydroxo system, all this type of system will have high lability in comparison to hexagon system.
जान के पिक्चर सब दीटा जगह हैला गोटे फास्ट एक नंबर केस टा क्रोमियम आ गोटे लास्ट होची ए जो केस
हां कॉपर केस एंड आयरन D4 and D9 system there will be only Jahn level discussion. Similarly, if you compare another two system, hydroxo system, you see the D3, E2G3, EG0, D3, so these are same. Chromium is in +3 oxidation state. Chromium is in +3 oxidation state. Both are same. So here exchange rate constants are. You see,
तोड़ा high हो ना?
2.4 into 10 power minus 6. This is 1.8 into 10 power minus 4. So 100 times acceleration. There is 100 times rate acceleration. Due to hydroxo species, there is 100 times rate acceleration. So you have to carry out, suppose you want to do the chemistry of this, see very slow. If you increase the pH, then this species will increase. This species means rate constant will increase. Substitution rate constant will increase. So this is a technique you can use to make your reaction faster. The higher pH, if you carry out the reaction at higher pH, the concentration of this species will be high and the rate of the reaction will be high for substitution reaction.
बा रिवर्स भी कर परियो जेमते कोन कोन सिस्टम
स्लो करे अछि रिवर्स कर परियो एसिड बढ़े यार परसेंटेज बढ़े एसिड pH ता लो कर दो ये 8% बढ़े pH हाई कर दो 8% बढ़े
इंटेस्टाइन लो pH रोची मन कोटे नष्ट हो जाउची गोटे मन डिसोसिएट कर दिउची तापर के लो pH रे करबा ताले स्टेबल हो
बस कोडा तुम रेट कांस्टेंट मध्य pH अनुसार डिपेंड करो को pH रे को स्पीसीज रो दिस अनुसार रेट कांस्टेंट हो then concept of crystal field activation energy बतन एटा ठीक है आबो करते सॉरी बोल crystal field activation energy का की गोटा पड़ता मेरा एक्सचेंज रेट कांस्टेंट आ गई ना सॉरी कल एटा कांसेप्ट आ रहेगा कांसेप्ट अभी नेक्स्ट क्लास में रखना Next is CFT explanation. lability and inertness. CFT explanation of lability and inertness. D part. Earlier we have discussed what is D part. D part means dissociative part. What is D part?
Dissociative.
D part means dissociative part. If the coordination number is decreasing, then the intermediate or activated complex may be square pyramidal or trigonal bipyramidal. So suppose your complex is like this, L5M X. X is leading group. Then in the rate determining state, RDS. So you have L5M. This may be intermediate or activated complex. If mechanism is I, interchange, then it will be activated complex. If the mechanism is purely D, then it will be intermediate. So this intermediate can have two geometries. One is square pyramid, another is trigonal bipyramidal. Square pyramidal, the geometry can be square pyramidal or trigonal bipyramidal. If you have read VSCPA theory, then you know that TBP is more thermodynamically stable than square pyramid. Trigonal bipyramidal geometry, you will have 6 bond pair repulsion. Here it will have 8 bond pair repulsion. So this is bond pair repulsion is more here. So potential energy will be more here. Potential energy will be less here. So TBP is more thermodynamically stable than square pyramidal geometry. And at the first stage, square pyramid geometry will be produced. Octahedral complex is octahedral. Now look at this. Suppose the complex is like this. This is living group. Now if the living group is lost, then you get square pyramid. So first step is the formation of square pyramid. You see, square pyramid. This may rearrange, then rearrange. This may rearrange to produce trigonal bipyramid. This is T. So here, bond pair repulsion will be 8. Here, bond pair repulsion is 6. So if we calculate the crystal field stabilization of this intermediate and crystal field stabilization of the starting complex, if the crystal field stabilization of the intermediate is greater than crystal field stabilization of the starting complex, then the starting complex will be labile. So try to understand this. if the crystal field establishment of the intermediate is greater than crystal field establishment of the starting complex. So this crystal field establishment of the intermediate is more. Crystal field establishment of the starting complex is less. Then this complex will switch over to intermediate. Easily switch over to for intermediate. Therefore, the system will be labile. It is very, very important one. If the crystal field establishment of the starting complex is less, crystal field establishment of the intermediate is more than crystal field establishment of the starting complex, then starting complex will easily switch over to intermediate and the system will be labile. There is another term called crystal field activation energy. That is crystal field activation energy. Crystal field activation energy. So this is equal to crystal field stabilization energy. Crystal field stabilization energy of the intermediate oblique activated complex minus crystal field stabilization energy of the starting complex. Crystal field activation energy, this crystal field stabilization of the intermediate or activated complex minus crystal field stabilization of the starting complex. If crystal field activation is 0 or negative, correct. मनोकर एटा अछि एटा मनोकर अछि -10 माइनस एटा अछि -8 एटा माइनस रे एक्सप्रेस होय एटा भी माइनस एटा भी so -10 minus -8 so this is equal to -2 so crystal field activation is -2 degree potential of the equal to potential -2 degree होले सिस्टम ना labile बुझ पाले तो ये crystal field activation energy is 0 किंतु एटा D10 अछि एटा D10 अछि एटा D10 सिस्टम एटा D10 सिस्टम यार 0 तो दीटा 0 है कोन सिस्टम labile तो if crystal field activation is 0 or negative then the starting complex will be labile. बहिरे केते बहिरे उल्टा अछि एटा -8 एटा -8 पॉजिटिव दा क्रिस्टल फील्ड स्टैंडर्ड यदि पॉजिटिव रे एक्सप्रेस करिवो ताले एटा उल्टा क्रिस्टल फील्ड एक्सप्रेस एटा -8 नेगेटिव रे एक्सप्रेस करिवो ताले हम जेहतु नेगेटिव रे जनरल एक्सप्रेस करबा so if crystal field activation is 0 or negative then the starting complex will be labile. If crystal field activation energy is positive the system will be inert. The positive है सिस्टम inert. चलो गोटे एग्जांपल लाइक क्लियर करो गोटे एग्जांपल डिजिटल आर क्लास का गोटे एग्जांपल होला एटा एटे गोटे डिसोसिएटिव ता आज बुझो एसोसिएटिव का क्या एसोसिएटिव कोन है A path. So A path, what will happen in A path? A path, suppose you have a complex is Ln x plus y, red determining step, LMXY. So this may be intermediate or activated complex. So this is coordination number is increased. So this may be intermediate or activated complex. If the mechanism is interchanged, then it will be activated complex. If the mechanism is only associative, it will be intermediate. So here also, the crystal field establish analogy of the intermediate is greater than crystal field establish analogy of the
starting complex.
starting complex. Then the starting complex will be Lability. If crystal fields calcium the intermediate greater than crystal fields calcium the starting complex, then the starting complex will be Lability. So for dissociative situation, we will calculate it and then you will know. Energy levels of different d orbitals in square pyramidal geometry. So here two structures are possible. One is octahedral wedge or pentagonal bistructure. Octahedral wedge structure or pentagonal bipyramidal. Octahedral wedge is also called
Distorted octahedral.
trapezoidal octahedral. Eta अन्य नाम trapezoidal. Octahedral. Trapezoidal octahedral. Boire eta पश्चिम कुमार दास बोरे eta फरक थर eta octahedral wedge. Octahedral wedge structure कौन है हिंदी? octahedral wedge structure. Octahedral wedge or it is XY living group भी रहेगा, entering group भी रहेगा. M सागर XY कोटा नंबर 7 है का 1 2 3 4 5 6 7 XY कोटा प्लेन है. living group का बाहर जो entering group का रिमेन करो. इसे octahedral wedge और trapezoidal स्क्वायर पिरामिड में भाई तार एनर्जी केम देल स्क्वायर पिरामिड वाला है. देखो एटी मेटल लिगैंड बॉन्ड XY प्लेन रे चारिटा होची ताले d x² - y सर एनर्जी सबटु बेसी हो तापर z एक्सिस रे गोटे बॉन्ड फॉर्मेशन हो तापर नेक्स्ट एनर्जी आसीगो dz2 तापर xy प्लेन रे जेहन चारटा बॉन्ड होची सेले तापर एनर्जी आसीगो dxy आ सबा शेष रे dyz dzx तले केमता रहौ जे नले 1 2 3 4 5 सबुठ बेसी एनर्जी हो
dx2
minus y2 एनर्जी पर प्लस 9.14 डिग्री तापर आसो dz2 एनर्जी ऑफ द इलेक्ट्रॉन here 0.86 डिग्री तापर आसो dxy एनर्जी ऑफ e minus 0.86 तापर dy dz के एनर्जी e1 Nadandaka, let us explain. Now let us consider a D1 system.
सर स्क्वायर पिरामिड टा कोठी आछि एसोसिएटिव हला
Dissociative ना
हाइट डिसोसिएटिव
Dissociative this is square pyramid रे in D mechanic D path electric D path Nadandaka जिनसा बुझिबार अछि most important ना बुझिबार Now starting complex. Starting complex है बेटा. it energy है plus 6 dq. it energy है minus 4 dq. चला एक मोटा बुझिया. Now if you take a d0 system. d0 system है
0
E2G 0 EG 0. So crystal field stabilization energy of the starting complex 0. इडी किछि इलेक्ट्रॉन नाही माने क्रिस्टल फिल्ड स्टॅबिलायझेशन कोण जीव 0 आहे स्टार्टिंग कॉम्प्लेक्स आ इंटरमीडिएट हळे इंटरमीडिएट रे 0
सीबी 0
ताले क्रिस्टल फील्ड एक्टिवेशन एनर्जी इज 0 minus 0 that is 0
लाबाइल
तो लाबाइल D0 सिस्टम लाबाइल
1
D1 सिस्टम तो लेटी T2G1 EG0 तो लेटी हो इलेक्ट्रॉन टा इथे रहे D1 ला पण इलेक्ट्रॉन टा इथे रहे तो क्रिस्टल फिल्ड स्टॅबिलायझेशन
-4 dq
-4 dq लेटी कितना है माइनस
4.57
dq चलो हमें पहले कौन
এটা भी लाबाइल हो
देखो क्रिस्टल फील्ड एक्टिवेशन एनर्जी will be minus 4.57 minus 4 that is equal to minus 0.57 ताले कौन है लाबाइल कौनटा बुझो के देखो अब काहे की कोऑर्बिटेट का ऊपर रहउछि तळ रहउछि तुम बुझेली ना माइन अपन D2 सिस्टम का D2 सिस्टम वाले एठी गोटे इलेक्ट्रॉन रहबो एठी गोटे इलेक्ट्रॉन रहबो हला ताले एठी गोटे रहबो एठी गोटे रहबो ताले एठी D2 सिस्टम वाले एठी गोटे ताले एठी गोटे -8
भी लाबाइल हो
देखो -8 8.0 देखो -8.0 ला एठी लगते बीटा मिसे 4.57 into 2 इसका 14 तो 9.14 so this is
-9.14
9.14
-8
9.14 minus 8 तमरा plus 8 so crystal field acceleration
-1.14
-1.14 dq कौन है
लाबाइल
मतलब
d2 ପାଇଁ
बता d2 लेवल बता d3 आसे d3 सिस्टम है एटा केता आइबो -12
-12 dq
12 dq अच्छा एठी केता हो एठी गोटे इलेक्ट्रॉन पाइबो एठी गोटे इलेक्ट्रॉन एठी जीवो काहे कि पेयरिंग हले एनर्जी बेसी दरकार से इलेक्ट्रॉन एठी जीवो तला -9.1 पर 0.86 ऐड कर दे तो 10 वाला 1 9 के 10 -10
भी माइनस है
तब एठी कौन आ रहा है केला
-2 dq होबो
एटा -12 -10 is equal to +2 dq ताना कोन आइला इना
नहीं सर
हेलो नहीं
-2 ना
-10 सर उल्टा करो -10 plus eta crystal field acceleration of the intermediate -10 आगे -10 -10 -12 is equal to +2 dq so inert है अरे crystal field acceleration of the intermediate crystal field acceleration of the intermediate का -10 crystal field acceleration of the complex वाला -12 so -10 -12 धर पॉइंट धर बुझिलो कि -10 हमर कोन हमें कहले डिप्रेशन है
प्रोडक्ट माइनस
acceleration energy is equal to crystal field stabilization energy of the intermediate
अच्छा
intermediate minus crystal field stabilization energy of the starting complex
हां ठीक है +2
तो ये प्लस dq है प्लस dq माने
इनर्ट ला
ताने सेठी dq माने कोन पोटेंशियल एनर्जी ताले तार कॉम्प्लेक्स ता तो इंटरमीडिएट रे कन्वर्ट हो हमके एनर्जी दबा को पड़े एनर्जी दबा पले रिएक्शन स्लो हो एंडोथर्मिक एमती सब d0 रु d10 पता हमें नेक्स्ट क्लास रे कैलकुलेट करबा d0 रु d10 बोथ एसोसिएटेड
करी कि दियो अपन करी देखि एक कर परसेंट देखि
हां पता ना प्रॉब्लम कोन दिया लेट अस देम they can try d4 high spin and d5 dissociative mechanism d path and d path का भी एक्सप्लेन कराया है so they try d4 d5 d6 high spin एटा लॉस एटा d4 d5 high spin एटा d6 लॉस ट्राई करो करी
लाबाइल होबो कि इनर्ट
कोडा इन लेवल ऑफ एटा d6 लो स्पिन d4 d5 ऐसे आ सब कैलकुलेट करिया सब एसोसिएटिव रो डिसोसिएटिव दा कैलकुलेट कले अगर इंटरेस्ट हो काहे कि हम बड़ा आर्बिट्ररी कोइ पारे कोडा लेवल हो कोडा इनर्ट काहे खोज लेवल क्रिस्टल फील्ड एक्टिवेशन हम जो जान कोडा लेवल हो कोडा
बही रे किछि लिखि नै
नाही बही रो अछि एता भीतर पसिर अछि एक कॉटन ये अच्छी बॉयल लिखा ही सब ये डिटेल नहीं डिटेल कैलकुलेशन है कैलकुलेशन बहुत कम जगह